So I think it's time to get started. We're going on to the last seminar of the semester. And today it's my pleasure to introduce Bart Ripperda, who is a professor now at CITA. He got his bachelor and master degree from Eindhoven University of Technology. Then he got his PhD at KU Leuven, Belgium, and then he joined as a postdoc. He joined postdoc at the CCA at Princeton University here, and then in 2022 he joined the IS here as a Hubble Fellow. And today he will tell us, he answers us the question if we are there yet, answering about the multi-messenger signal in black hole simulations and in plasma universe.
Thank you. And yeah, it's a pleasure to be back and to see everyone again. I'll try to go through some recent developments of what we were able to do with combining magnetohydrodynamics and particle and cell simulations of plasma around the universe, around black holes. And as Jim pointed out, this work was done with all the people that I'm not going to name, but my students are in the top, so I definitely want to highlight them. But I have pictures. So why do we care about black holes now? I don't think this is the crowd that I need to convince, but I still want to highlight some recent or less recent observations. We obviously have the Event Horizon Telescope image with polarization that tells us something about the magnetic field structure from MED7 Sagittarius A star. From Sagittarius A star, we have very well resolved flares over a range of wavelengths. With polarimetry measuring the orbital motion of emitting flare, and now with James Webb having a very well time resolved light curve of the flare. But we also have more distant objects. We have X-ray coronae from both XRBs and more luminous AGN, like Seyfert galaxies, well, I'm saying it's a tentative neutrino detection from a Seyfert galaxy because there's quite some debate, but it's definitely interesting that there seem to be neutrinos coming from the inner region of an AGN where we also see X-rays coming, and this comes without gamma rays, so that's particularly interesting. Hence, that it's an optic coming from an optically thick corona-like region. We have from last year a changing look AGN that shows a real-life launching of a jet. Here you can see it in the yellow. And while the jet is launched, you also see the corona switching on suddenly in hard X-rays, which hints at that there may be a mechanism that can magnetize the inner region such that you get a coronal emission together with the colloidal field that can launch the jet. And I'm studying this inner region of the black hole, where we get some hints of how these phenomena can be powered. I also don't really think I need this slide, but I still want to go over it. So these plasmas near the horizon are relativistic, which means that we have a lot of magnetic energy density compared to rest mass energy density. That's the opposite regime from the Earth. Or even the sun, where your sigma parameter is smaller than 1 or tokamak. It's somewhat similar to a neutron star magnetosphere, particularly for the jet and maybe the corona-like region or the magnetospheric region close to the horizon. But the accretion disk itself of the black hole is not necessarily at very high magnetization. So relativistic effects there are less prominent the further away you get from the black hole. What does this mean? The plasma is typically collisionless in this high sigma region, not necessarily in the accretion disk, but definitely in the magnetospheric regions. Mean free path is large. The large magnetization means that our alpha speed typically goes to the speed of light, and we can get large Lorentz factors. And the scale separation is tremendous. Typical particle motion and skin depth are much smaller than the system size. So that means you have a large reservoir of magnetic energy, and you have a lot of potential for particles to accelerate because of the large mean free path. So all the ingredients are there, but that doesn't tell us yet how they energize and how they radiate, because a magnetized plasma in itself doesn't necessarily have to radiate. You need to find a way to extract that magnetic energy and put it into photons. It's a difficult question. You need special relativity, general relativity, you need kinetic theory because of the collisionless nature. You need some radiation and potential quantum electrodynamics to model the radiation and the plasma radiation interaction. And all of this is of course, highly nonlinear. And so typically analytically, we cannot get to the answer. So we need high resolution simulations. The difficulty I want to emphasize is not that we don't know which equations to solve, it's that the difficulty is that they're hard to solve. So this is a set of equations that we want to solve. I left out GR because probably on particle scales, GR is not too important. So this is the Vlasov equation here, evolution of the distribution function of whatever particles you think are in your system. The Lorentz force, the electric and magnetic fields you get from Maxwell's equations, and the distribution function, the particles feed back into the charge and the current. So this is closed system, can be solved with particle and cell, but on the global scales, that's very expensive and difficult. The reason for that is that, as I already mentioned, there's a huge separation of scales. If you look at MED7, kind of like a canonical object to think about, the jet that we're seeing is over 1,000 light years long. The inner region, let's say the Schwarzschild radius, is about 0.006 light years large, but the Larmor radius of a particle is about 10 to the minus 11 times that Schwarzschild radius. So there are, if I count correctly, 17 orders of magnitude difference there that we cannot capture with kinetic simulation. So there is no global 3D kinetic simulation of a black hole accretion disk. I think there are a few efforts, but coming up. So you may have seen one, but still there I want to emphasize that the scale separation is artificially shrunk to maybe 2 or 3 orders of magnitude. We know that large and small scales interact. Also don't need to think, I don't need to convince you that turbulence can do that. So we cannot simply ignore the scale separation. But we can use magnetohydrodynamics, which is in some sense scale-free, to capture the global dynamics of the accretion and the jet launching. At least we think that magnetohydrodynamics can capture that. And what I try to do is to improve magnetohydrodynamics with some kinetic effects to get a better sense of what's happening at the subgrid scales. MHD, mass, energy, and momentum conservation, still with Maxwell's equations. Here I added a GR because on MHD scales, GR is typically important. We get by taking moments of the distribution function, we get a reduced set of variables, mass, density, velocity, energy, and we still keep the magnetic and the electric field. What's typically done is then assuming ideal MHD. So we assume the plasma is collisional. It's typically wrong in the magnetosphere. It means you get a single temperature Maxwellian, electrons and ions equilibrate, which is also wrong. Ideal MHD also assumes the plasma is a perfect conductor, meaning that in the fluid rest frame where the velocity is 0, your electric field is 0. So this means there is no accelerating force. Magnetic field does no work on particles. You really need that electric field. I went one tiny step beyond ideal MHD by adding a resistivity. And if you do that, you actually need to solve an additional equation that is Ampere's law, or actually Maxwell's equation, because Ampere didn't get it fully right. Not blaming him, just this history. This effectively means that you have an Ohm's law here, which accounts for the dissipation of magnetic field and the formation of a non-ideal electric field through resistivity. So this is the simplest way of getting reconnection physics in your MHD system. Makes it easier than particle and cell, but still not very easy because you still need to resolve that resistivity, which requires a high spatial and temporal resolution, because resistive timescales are very different than advection or ideal timescales. So you have two timescales in your system, and you need to do that in a circuit. I use an implicit method for that. I can talk about details if you're interested. Right. That still doesn't give us particle acceleration. It just gives us potentially a mechanism for that particle acceleration. So now that we have the theory done, let's go look at low luminosity black holes, ME7 and Sagittarius A star. I already mentioned all of this. I think for Sagittarius A star, but I also want to emphasize that ME7 flares at even higher energies, so gamma ray flares every so many years, every 2 to 3 years, depending on if we're lucky enough to catch it, because we're not continuously monitoring them. So we have discrete measurements. So it may flare more frequently. We may just miss it. Right. So what do we think is happening? Often invoked by observational papers is reconnection, solar flare. You see there an example from the sun, artist's impression. And from the sun, we know that magnetic fields reconnecting can accelerate particles. We also know that cannot happen on a black hole, because a black hole cannot form a closed loop that would violate the no-hair theorem. So the black hole itself doesn't have magnetic field. The magnetic field needs to come from the surroundings, whereas in the sun or in a neutron star, the magnetic field can come from the object itself.
That's a question. Isn't the hair theorem is only for static configurations? So if something is actually happening, like accretion?
No, that's correct. Yeah, so you can. So first of all, it's like a plasma variant of the no-hair theorem. It's not the GR vacuum no-hair theorem. But what it says that any loop acquired by the black hole needs to decay exponentially. So it needs to get rid of the loop on an exponential time scale.
Even if it's not static configuration?
Yes. Yes. Yeah. And it's also what we see. That's exactly what the simulation does. So I think the main point I want to make, that there is a distinction between the sun that can generate its own loops, whereas the black hole needs to acquire it from the outside, I think. And then the no-hair theorem just makes it sound cool. So in the sun, we can nowadays observe this actually in detail. And this is a from 2022 Nature paper. In H alpha, you see what they interpret as two field lines that approach each other. And here they reconnect, they form an X point. And then they see these bright blobs, and they interpret those blobs as plasmoids, which sounds intriguing. I don't know if they are plasmoids, but you definitely get radiating blobs, which is what we also see in simulations of.
How do you measure time here? Because the C happens later than before A.
It's a good question. Yeah, that's a good question. I never noticed that. I never noticed that. In the paper, they definitely explain that time step. One is a result of the other, but I should check this in. Very interesting. Maybe that is a different reconnection event, because there's probably many, as you know, like it happens continuously. But yeah, I'll check the paper over dinner. So now the question is like, can we trust those one-zone models of reconnection powering flares near black hole horizons? Or and if so, like where exactly and how exactly does it? This is a PIC simulation by Greg Werner. You see the plasmoids. I don't think I need to explain this in too much detail for this crowd, but what I want to show effectively is if you do this is plot by Lorenzo Sironi, if you do a PIC simulation for a connection, what you see is that the energy of the particles scales with sigma. So you see that the power law tail changes and the maximum energy of the particle goes up. So if you have reconnection happening at higher and higher magnetization, you can get more and more energies, more and more high energy. up to the point that radiation starts to become important. So you can accelerate particles until they start to radiate, and then the radiation cuts you off at a certain point. This is very promising for black holes because close to the black hole, you may have sigmas of 10 to the 8, 10 to the 9 potentially. So there's a lot of space to accelerate. How do I think that happens? So I'll go back to Blanford and Znayak, theoretical picture. Colloidal magnetic field falling onto a black hole that is spinning. The black hole winds up the field. You get out of plane field. You create an electric field that launches a jet. But this field line here will get quenched, and that is where potential reconnection can happen. Sasha Tchaikovsky, among many others, has shown that that such a jet is actually launched in this way in GRMHD. This is what I said before, that GRMHD can capture the basics of accretion and jet launching, but there is no reconnection visible here, even though these field lines will be anti-parallel. So we probably need higher resolution. Just to show you a picture of what could happen, this picture by Ashley Bransgrove. As long as the black hole is accreting, you have ram pressure that is exceeding the magnetic pressure. So the gas can fall in, drag magnetic field lines with it. The field lines are being wound up. So you're accumulating field lines here, powering the jet. But the field lines, because this is very magnetically insulated, the field lines will not migrate to the spine. They will accumulate here in the boundary of the jet, create magnetic pressure that will push the funnel, accretion funnel inwards, until the point that your magnetic pressure starts to become equal to the ram pressure. At that point, your inflow funnel has become so thin that you kind of have the inverse of a solar flare. Coming back to Lena's question. So in a solar flare, the field lines would originate, the foot points of the field lines would be on the sun, and then they would close somewhere here. Here it's opposite. The foot points of the field line are on the disk, and the loop closes inside the horizon. So it's an inverse loop, but it doesn't matter as long as you cut it off, you get reconnection. And this field line has to be anti-parallel because it's the same field line. It's a loop, right? It goes in here, closes here, and it goes out here. So if you can get those field lines to be close enough to each other, or the field line to be close enough to itself, then you may be tearing unstable. That happens. This is a simulation by Ashley of a loop that's put on a black hole, and you see that it does exactly what he expected, or we expected. And there's an interesting effect, which Wikipedia already nicely points out for us. If you think these are the two jet bases, northern jet, southern jet, the field is horizontal. In reality, it's sort of like a spiral current sheet, or maybe not so obviously, but the field is wound up. But if we stay in plane, it looks horizontal. The horizontal field reconnects, and what reconnection does is it creates a little bit of vertical field, independently of the black hole. Now imagine here is the black hole, that field will fall in, but these loops here, they're able to escape. And they get towards the accretion disk. So you're creating vertical field that can push your accretion disk outwards. You're creating a vertical wall that can stop your accretion disk from falling in for a certain period of time. So this is the way you can sustain this reconnection. The reconnection can sustain itself by creating a vertical wall that protects. You see this in local box simulations as well. You're creating here a vertical field in the exhaust or the reconnection on both sides. There's no black hole here. So how do we resolve this? This was a 2D simulation where we have a resistivity and we make sure we resolve it on the grid. We use mesh refinement, which you can see here, 6 or 7 levels, I don't remember. You nicely see the turbulence. This is 2D, by the way, so there is a lot of physics missing, just to make the point. If we zoom in further, at some point we see indeed the reconnection happening near the horizon. We zoom in further, and suddenly you see that you just have a reconnection layer left that looks an awful lot like that local box picture that I showed before. You have plasmoid mergers. The reconnection layer is obviously not completely straight, but it's very well resolved by the grid. The reconnection rate here is 1% of the speed of light, so it's 10 times slower than in particles.
It's mesh, which is
It's the grid. It's a numerical grid, yeah. Yeah, but the weird patterns here are due to the projector, like the just
some sort of atheism.
I think so, yeah. Yeah, exactly. I had this same question recently and I didn't even notice it myself, but yeah, it's definitely not some weird complex mesh. You should
Could
clean
you
that.
run it again?
Sorry?
Could you run the whole thing again? That was beautiful.
You must have seen this like a million times.
I still love it.
Here you actually see nicely that the grid is properly structured and not. So we zoom in, you see a lot of nice turbulent features. We zoom in further. You see actually very large plasmoids. There is one here, for example. I think that's a bit of a 2D artifact. In 3D, those plasmoids don't seem to grow that big.
This is resistant.
This is resistive, yeah, that's right. Yeah, but uniform resistivity, nothing special yet.
Does it matter? Like if you didn't have resistivity, would you still have?
No, it doesn't matter. This is
Sorry. Say it again.
so uniform resistivity versus ideal MHD doesn't matter as long as you have large enough resolution to be in an asymptotic Lundquist regime. So if your cell size is small enough to have a numerical resistivity that gives you a Lundquist number of 10 to the 4, the reconnection rate is the same, the plasmoids look the same. So we tested this in the local box, a paper by my student Michael Graham came out earlier this year, where he did force-free ideal MHD and resistive MHD, and it all looks the same reconnection rates and all. So yeah, numerics kind of finds a way to reproduce.
The ideal MHD would depend on your refinement level.
That's the thing. That's the main thing where you, so here, and you also depend on your refinement level in the sense that you need to make sure that you're resolving the resistivity. And in ideal MHD, it's kind of like shooting in the dark, hoping that you have a high enough resolution to capture that. And of course, like, you know, like here, the reconnection layer is very well resolved, whereas in ideal MHD, it will be on the single cell level. But I don't think that's the worst thing, to be honest. Because this was the first time we were studying this, we wanted to make sure that we were resolved. This is the 3D equivalent, and that immediately answers your question. And this was with ideal MHD. And still, you will see, if we zoom in, that you get, reconnection layer, which is now 3-dimensional and more turbulent, and you get plasmoids that are 3D-like, so they're actually little tubes that are kinking and so on. But overall, the physics is the same. Now, this changes, and I'll try to make this argument later if I get to it. If you actually want the collisionless reconnection rate, if you want a 0.1 rate, you will need to do something special with your resistivity. It needs to be spatially dependent. It needs to particularly peak in X points, and that cannot be done with ideal MHD, or you would have to design an AMR criterion that gets you a non-uniform resistivity exactly in X points, which seems not very feasible. In any case, so in 3D, we also get this reconnection layer. You see it's highly non-axis symmetric, as in it's different left and right of the black hole. You also see, I didn't put field lines here, but you do see that the accretion disk is pushed all the way out. That's by this vertical field that I was talking about before. So the reconnection may be a nice flaring mechanism, but it also does affect the global dynamics. And this goes in cycles.
What's the radial scale when you say pushed all the way out?
Oh yeah, good question. Yeah, so it depends on the flux eruption. Let me maybe go back to, skip this. So this is the flux on the horizon versus time. Ignore this part is all transient. You see that typical eruptions, reconnection events, they last about, say, 100 Rg over C. So purely from your reconnection rate, you can then invoke how long your reconnection layer needs to be. But you see that there are smaller events and bigger events. And even if you zoom in, you see there's tiny events were also the flux ropes. So you get a range of lengths of current sheets. They all, so not only in length, but also in azimuthal angle. So the longer the current sheet gets, because the thing is like spinning around, the longer the current sheet gets in radius, the larger like area it sweeps out in angle or in r phi. So this is the one that I'm showing, this final one, and that sweeps out. That's about the largest we have seen, and that sweeps out a very large fraction of the full 2 pi up to 10 RG. So the whole inner 10 RG has only a current sheet.
These cubes got larger and larger.
Say it.
Don't you have a feeling that these the moment when they're
Get larger and larger, right? So there is if I have time, I'll show something about that. The thing is that these flux eruptions, they do affect your surroundings because you're pushing magnetic flux into your disk. So you're magnetizing the disk in a sense. So the next flux eruption will be pushing stuff in a more magnetized disk. And some of that field is recycled. So it reaccretes, but that's about 10%. We have a paper upcoming with Christoph and Olajko. So you reaccrete about 10% of the flux. And the rest is new flux that gets in by really little instabilities that can go around the vertical field. That makes it more obvious that those flux eruptions will start to differ in time because you push out the flux into a different disk than it was before, more magnetized disk. So the eruptions can probably get bigger, but we still see, we ran this now, instead of 10,000, ran it to 100,000 RG over time. We still see a stochasticity in the size of the flux eruptions, which is kind of nice because if this is indeed a flaring mechanism, the flares that we see are also not always big. They're also stochastic in how long they last and how powerful they are. But it's a very good question, like what's the steady state of this thing? Like, I don't know. Another thing to note is that typically these simulations are only in kind of steady state accretion up to maybe 10 or 20 or 30 RG. But you would want something that's fully MRI resolving up to very large radius. So one big question is like, does this actually happen if you have a realistic feeding mechanism? This is something that I think Jim and Gao have worked on, also Sean Ressler. Yeah, I think there are some good indications, but definitely not trivial.
So why is it asymmetric?
Why is it asymmetric? Yeah.
Like on both sides, if you look at the just the length of the current sheet is different on one side versus the other. I mean, just
because it's 3D.
Okay, but will it flip at some point?
It's spinning around. Yeah. So like if I show you a later point in time, this thing will have moved around. It looks like a big spiral.
Yeah.
3D. So the spiral starts at like the current sheet starts at a certain angle and then it goes around. So it gets bigger in radius while it spirals out. Like think of a field line at the base of the jet. In essence, these are the field lines at the base of the jet that are like and going up. So you will automatically see that in 3D that field line goes larger and larger radius the further you move along the field line. So yeah, this happens in duty cycles, like Sasha pointed out. What you see is that the plasma feeding the current sheet is highly magnetized. This is an MHD, an artificial magnetization. It's not as high as it would be in reality because you need some foreign mechanism or whatever, but you can extrapolate to real magnetizations and then do analytics. Right. So Alisa here in Princeton did a general relativistic particle cell simulation of such a system that gets magnetically arrested in a simplified manner. It's two-dimensional. All the material is falling in radially, but she found that also then you get magnetic arrest and you get the current sheet here. And the reason I want to point this out is that she was able to do an electron, positron, proton plasma, and this is the proton density. So what you see is that the proton density is high in the accretion region, but low or zero in the current sheet region. So the current sheet is really fed by pair plasma coming from the jet, which we're not capturing in MHD. But then Hayek, who was in Princeton before, but is now at the CCA, simulated such a reconnection layer in a local box particle and cell simulation, incorporating all the necessary physics to get out the radiation. So he included synchrotron radiation, inverse Compton, and also pair production, because we think there's pair production happening here. And then, this looks something like this. This is what you've seen before by Greg Werner's simulation. These are the photons. And now actually you see that plasmoids seem to light up as bright, which resembles this solar picture, which apparently is acausal in time. What Hayek could do then is get the spectrum, photon spectrum from this simulation. And what's quite interesting is that you see a large bump here from the synchrotron, and the large bump peaks in the X-ray. And from the inverse Compton scattering, particularly inverse Compton scattering on seed low energy photons, he sees a higher energy bump that gives you a gamma ray. So this could be a mechanism to explain the simultaneous X-ray and gamma ray flares from MED7 if they come from near the horizon. Now, this has not solved the problem, obviously, of what powers those flares. It's more, I would say, the other way around. It shows that reconnection near the horizon could potentially power a subset of flares. Anthony Chow, grad student at Columbia, has taken this a step further because it's not obvious from Alita's picture that there are absolutely no protons in this region. And this is something you can measure in MHD. There is also a paper by George Wong and Jim, where they measured disk material mixing into the jet. We specifically asked how much disk material ends up in the reconnection layer near the horizon. So Anthony again did a 2D simulation so that we have very high resolution, resolve the physics, and he put a tracer in there. So he's tracing disk material versus jet material. And he wants to see how much disk material is in the jet. So orange is disk, blue is jet, and you see things reconnecting. And the initial stages of the reconnection, there is still a lot of disk material in there. See if I play it again. You see the plasmoids already, very orange, very proton dominated. At some point, you get all the protons out of there because they advect with the reconnection flux. It's still reconnecting now, but now it's purely the floors. It's purely the jet flux. Now in reality, it would be paired plasma. And this happens again at the next accretion event. You bring in new protons. And if you think of that flux eruption, so the flux going down, what we see is that the initial part of the flux eruption is still proton dominated, but the final part is a very pair plasma dominated. So this may give you a succinct like signal. And again, Hayek simulated this with a PIC. This is actually based on an original simulation by Sasha here, who did the first electron proton simulations with synchrotron cooling. What was found is that somewhat dependent, but minor dependence on what the fraction of protons is, which we can measure from this simulation here, 0.5 and 0.15. You see that the electron-positron spectrum and the proton spectrum, they differ, different power laws, but the protons can accelerate also to quite high energies, so they will also start to emit radiation through synchrotron. And that gives you an additional bump here. So this is the previous synchrotron X-ray inverse Compton gamma ray, and now the ions can do synchrotron, which gives you a GeV signal. And that GeV signal can potentially be seen from ME7. Yeah.
Brought electrons and positrons recombine,
Into pairs, yeah.
and then you have emission from that.
Yes, yeah. We didn't plot it here, but you see it. That's this line. Yeah, but it's probably not luminous enough to see, but yes, it definitely happens. Right, so this is more of a prediction, and with ME7 flares, there's a campaign coming up for a video of ME7 where we can monitor it for a longer time and hopefully capture a flare. If we get Fermi probably Fermi to look, we may be able to see such a GeV counterpart of the flare. There's some indication that the flare from 2019 shows that GeV part, but it's not obvious.
I shouldn't worry that they look like there are data points much below the curve, should I?
It's not obvious how this is normalized. It's not. That's what my observer friends tell me. So I wouldn't conclude anything based on that. That's effectively what they told me.
This is just the average of many.
That's the thing. It's just over a larger period of time. So the flare event is in there, but it's yeah. That's why I call it a prediction and not a explanation. Right. So what is particularly interesting is also if you're accelerating protons here, they may end up in those big vertical fields and in the boundary of the jet. So this could be a mechanism to get already accelerated protons injected in jet boundaries where they could further accelerate and potentially become cosmic rays. That's interesting to think about. Right, so Siddhant Solanki at Maryland then took these results, the particle cell results, and the electron distribution function, and painted that back onto the GRMHD simulation. So we took the current sheet, he isolated the current sheet in the GRMHD simulation, and shot photons from that current sheet with the right energies, and the angles as expected from photons emitted from a reconnection layer, and traced them. And that way you can create a light curve. That light curve will depend a bit on the beaming properties, like how much are the photons shot along the field or not. But what you see is that he gets let's look at this one. He gets a light curve that particularly peaks during the flux eruption event. It's significantly higher than the quiescence. But the main thing you will see is that it's not only very stochastic, and that is because the current sheet is doing this. So it's not obvious that you will, during the whole flux eruption, capture the photons. They may be, shot away from you. But also the event here lasts, what is it? Maybe good estimate, say about 100 days. Whereas the latest ME7 high energy flare that we saw with the EHT multi-wavelength campaign, it lasts, what is it? By good approximation, maybe 10 days maximum. So there is a discrepancy here in how long the flare lasts. That can be due to a number of things. That can be due to beaming and lensing effects. It can be that we're only seeing one of these peaks. But if you were to ask me for my best bet, I think it has to do with that the reconnection rate is slower in amplitude. The reconnection rate in amplitude is about 1% of the speed of light, whereas in peaks about 10% of the speed of light. So if you're reconnecting faster, the flare will end faster. This is something that we see in ELISA's GRPIC simulation. So it will last for a shorter time. So it's cool that we can do this, but I think it would require further studies with better, more realistic reconnection physics. Another interesting prediction comes from Haja, who was an Elliott student here when I was still here. He, together with Kaushik Chatterjee, I should say, ray traced this simulation now for the lower energy emission, so the sub-millimeter, to see what happens with the Event Horizon Telescope image during a flux eruption. And the kind of obvious expectation would be like, oh, we see a multi-wavelength flare, so we also see a flare in the sub-millimeter. This is the standard EHT ray tracing. The thing looks bright, still accreting, and at some point you will see the flare happening. But now, what's quite interesting is that during the flare, during what we expect to be an X-ray flare or something, we see the image actually dimming. And that is because you push that accretion disk outwards. So your accretion disk sits beyond 10 while the EHT is observing the inner 10 So you're not seeing much emission from the disk anymore, except the photons that really make it inwards from the disk and go into the photon ring. And the current sheet is the main emitter, but the current sheet is very hot. So the current sheet will, the power law from the accelerated electrons will extend to low energies. So the current sheet may be emitting also sub-millimeter from non-thermal electrons, but they will be very non-luminous. So likely you won't see much from the current sheet, and you won't see much from the disk because it's pushed outwards. So He also produced a light curve, and the gray bands are the time periods where you have a flux eruption. And you see indeed that the sub-millimeter flux significantly drops there. Well, this was still simulated with assuming a thermal distribution for the electrons. So this should be redone with more like CITA did, where you take into account the distribution we expect for the electrons in the current sheet to see if there's actually a signal. But it's quite interesting to look for a dimming effect during the next very high energy flare that we see. For Sagittarius A star, there seems to be a little hint of this happening, but I wouldn't dare calling it more than a little hint. This is a light curve observed with ALMA by Maciek Wielgus. Here there was an X-ray flare, and you see that the sub-millimeter light curve goes down a bit. But as Lena can tell you better than I, this is all very stochastic. It's hard to see her nodding. No.
I agree. What do you about?
So it's very hard to theorists speaking, it's very hard to link this both in space and in time to the X-ray flare, and it's even hard to say whether this is actually a peak or just a variation of the sub-millimeter. But I do think that if we keep observing multi-wavelength MD7 and Sagittarius A star, we may get an idea of whether this dimming actually happened.
Was it not observed during the flare, or is it not detected? There's no where the X-ray flare is, and there's no points. Is that?
I think it was not observed. Yeah, I think it was not observed. Yeah. We have a lot of new data with James Webb. So we can look in the mid-infrared. This for Sagittarius A star. Sorry, I'm jumping a bit back and forth. So I want to say a little bit about Sagittarius A star. This is work by Sebastiano von Fellenberg, who's at CITA. And he has JWST data of Sagittarius. And this is a light curve of a flare in the mid-infrared. But because of the very nice properties of JWST, this light curve is not only very well resolved in time, but he can also measure the photon index during the flare, the change in the slope of the SED, of the photon energy spectrum. And what you see is that during the rise of the flare, you see that the spectral index changes. It goes up. It changes sign, actually. It goes from down to up. Once the flare has reached its maximum, it stays up there for a while. And then at some point, you see that it goes down again here towards the end of the flare. So the way we interpret this is that this is the onset of the flare. Here we start injecting accelerated electrons by whatever mechanism I think is active. But the cooling time in the infrared is relatively slope. So the cooling time only starts to be effective here halfway through the flare. And that is where you start seeing the photon index going back down again. So you see the effect of the injected electrons first, and then the effect of the cooling where the photon index goes down again until you reach the end of the flare, and then it goes back to a quiescent-like spectrum. The end of the flare is not obviously related to the cooling time. It's most likely related to the mechanism ending, the injection mechanism ending. And I'll say something about that next. So again, with more data, we will be able to extend this to hopefully simultaneous submillimeter and X-ray flares or absence of flares. Because Sagittarius A star shows X-ray flares about 1 in 4 times compared to the infrared flares. So there must obviously be something going on that some flares can power, can also be powered in X-rays, and some flares cannot. It can mean different mechanisms, or it can mean strength of the flare because the mechanism is, for example, your current sheet has different properties. So my student Braden Seefeld-Gale has simulated pretty much the same as I did, but for a range of different settings. So this is a magnetically arrested disk, but he did different spins, and he also did Bondi accretion. And the interesting thing is he added in this tracer that that Anthony did in 2D. But now he has been looking at a flaring mechanism for Sagittarius A star. And Sagittarius A star doesn't have an obvious jet. It may have a wind that Lena had this very nice paper out recently, but at the it doesn't have an obvious jet like MD7, so we don't really know what happens exactly near the horizon. But it's less likely that this flaring mechanism near the horizon works. And the reason is that the X-ray spectrum that we're seeing has a certain slope, and that slope is very different than what you expect from high sigma recognition. That could be brought closer together if your reconnection would have a guide field, which is unlikely if it's a spiraling current sheet, or if there was a significant fraction of protons there, which is also not obvious. Something we're working on is not obvious. So, but for Sagittarius A star, we also have seen with polarimetry the orbital motion of a flare, and the current sheet is also not obviously rotating. So we started thinking about different mechanisms, and those current sheets are ejecting that vertical field, and that vertical field remains hot, and that actually seems to orbit as a flux tube. So that's what Braden studied. And the tracer will tell us how much jet material, how much electrons and positrons are left in that flux tube. You'll see density here, magnetization here, and this is a tracer of the jet materials. Yellowy is material that originates from the jet, so floors, but think electrons and positrons in reality. Here we go. The thing will, oh, we're looking top down now. I'm sorry. So here, like flux eruption event happens, it blows out this tube. There are a couple, one after another. Here's another one. So the vertical field I was talking about before is now out of the plane. And now in a little bit, there will be a very big one, I think. So what you can see is that this whole inner region, due to multiple flux eruptions, gets very, very magnetized. So that relates to what you were asking before. So if you keep doing this many, many times, the whole inner region may at some point get completely dominated by those flux tubes. But here you see a big one. It's clearly orbiting. It's clearly still magnetized. It's clearly still filled with jet material. And you see that there's a couple of instabilities at the boundaries. You will see Kelvin-Helmholtz-like structures because it's shear. And you see Rayleigh-Taylor-like structures here that are making it inwards. So those Rayleigh-Taylor structures, if you think of a Rayleigh-Taylor plume, they may also reconnect. The Rayleigh-Taylor plume, if the field traces the Rayleigh-Taylor plume, like it will reconnect on itself. So also here, you expect reconnection events that may accelerate particles inside the orbiting tube. You see this also here from a side view. Looking from the side again, here the reconnection event will happen. This temperature, you see that it gets hot. It blows out this flux tube, and you see that the flux tube is still hot, and you see that the flux tube really has a vertical field, whereas here on the other side, there's no flux tube, it's really turbulent field. Now this vertical field will orbit and will confine particles. And here you see the 3D kind of version of what Braden showed in his previous movie, and also here you see these Rayleigh-Taylor fingers forming. So this is particularly interesting because now we have a tube with electron, positron, plasma at moderate sigma. It's not as high sigma as the jet anymore. You get Rayleigh-Taylor that mixes in some protons. And there's a guide field because the tube has vertical field that's not reconnecting. And you're accelerating particles. So suddenly you have all the properties to explain flares from Sagittarius A star. So what Vladimir Zdankin did, and his current student, who's also named Braden, but it's not my Braden, Braden Buck, don't have his picture. Vladimir simulated this in 2D and they're now simulating in 3D. I don't have a video of that. So this is the boundary of the flux tube with particle cell, high density, low density, and you will see that such Rayleigh-Taylor plumes will suck in particles. These are particles. Here they start to reconnect because you smash together two tubes, and this accelerates the particles. You get a power law here, and the slope of that power law, if you think that those particles would emit in synchrotron, you can take your Rybicki-Lightman, then the slope of that electron distribution function gives you the slope of the photon distribution function, and that matches roughly with what we are seeing for Sagittarius A star. Now again, this hasn't solved the problem. We need to do this in 3D. This was actually electron, positron plasma. You need to have protons in there. You need to vary the angle of your magnetic field and so on and so on. There's still many open questions, but it's a very promising mechanism to study further, I would say. Because I know Jim and other people are interested, and I wanted to say a little bit about luminous black holes. Only one slide. Work done by Jibba Musoki. So if you start with a large accretion disk with a lot of flux, then it seems that also a thin disk can get magnetically arrested or truncated. It's unclear to me, or it hasn't been mapped out yet, when exactly this happens. But at least if you start with a thick disk with magnetically arrested initial conditions, so not that it is magnetically arrested, but the initial conditions that would make it magnetically arrested, and then you cool it down, then you get what's dubbed a truncated disk that has a lot of similar properties. So you see now here a thin disk, and you see that again, the horizon is separated from the thin disk by reconnection. The difference is that now the flux doesn't drop in huge eruptions. It drops kind of in very tiny reconnection events. The current sheet stays there kind of all the time, and it's very axisymmetric, even in a 3D simulation. So you're blowing out flux over the whole azimuthal angle. So you're creating this vertical field, but now over the whole angle, so you can keep your thin disk out. But because the disk is thin, the vertical field is not really vertical. It looks more like a C. So it wraps around the thin disk and it keeps it out for an extended period of time. Also here you see that accretion seems to go through Rayleigh-Taylor events, which still manage to go around that barrier. So this is something that Jibba is wrapping up right now, and this could be an interesting model for black holes that show corona emission, but also a strong jet. And definitely not all black holes with coronal emission show strong jet, so this cannot be the one and only model, but it's an interesting one to think about. And I still wanted to show that. I didn't really get to multi-messenger, but all of these things also happen around merging black holes, but that's for next.
Sorry, you mentioned accretion goes through some Taylor events.
So what we think to see is that the accretion in the inner region is not MRI driven. So here it's still MRI driven, but the accretion that can make it through this magnetic barrier seems to go through interchange instability between the magnetized inner region and the higher density outer region, gravity points inwards. So we see those radiator plumes that manage to penetrate the magnetic barrier or go around it. And then they become streams and they make it all the way to the horizon. So that is, for now, more of a heuristic picture, like we think we see radiator, but we're doing linear stability analysis to actually make sure that it is. Yeah.
Different from accreting stars?
No, I think it's very similar. Yeah, probably even if I,
If I reverse it.
It's like reverse, yeah, and like particularly neutron stars that don't have a strong dipolar field, I think would look very similar. If there's a dipolar field, you would probably have the same, but the accretion funnel would be guided along the dipole. But yeah, I think it's very similar mechanism. That was all. Thank you.
Yeah, we have a situation, so.
Could you repeat again, why does this simulation show a jet and your previous disk simulations weren't showing a jet?
They were all showing a jet. Yeah, they were all showing. So this is another topic that I didn't really get to talk about, but for Sagittarius A star, you would want to come up with an explanation why we're not seeing a strong jet. There are several ideas out there. It may be that the jet has existed previously and we see remnants of it. You should talk to Lena, who knows this much better than I. It can be that the jet is there, but it's like not luminous, as in it's very low particle density. You don't see radiation from it. But it can also be that the inner region may be magnetically arrested. So it forms a jet, but the jet can never break out. It kinks before and dissipates before it reaches any reasonable distance. And this is what you see in like the wind-fed simulations or the Bondi simulations by Sean Ressler and Elisa, that the jet is destroyed.
Any difference in the jet efficiency between them and like this? Or
yeah, I think there are differences, and it will depend exactly on how the thin disk is initialized. I think one of the interesting effects is that if you don't truncate, if you are toroidally dominated in the accretion disk, then you don't see a strong jet. It's kind of obvious there's no strong colloidal field, and then you get more like a sandwich type corona without a strong jet. But related to my first slide, we see that for this changing look AGN, the jet suddenly switches on. So I would say the question is like, is there a way to switch on and off the jet in such kind of systems? And one thing you could think about is that you would, something that we typically don't simulate, but you would be accreting multiple loops with opposite polarization. So you would get kind of a striped jet that switches on and off. I think those are things that we're exploring within SEEKS, but yeah, I don't think there is a conclusive answer yet of how to do that. But I think that what you're asking is at the crux of it, like what happens to the jet? Why is it there? Why is it not?
There was once in a 3-hour plasma seminar where a mathematician claimed you can't formulate any viscous or resistive relativistic theory. Doesn't make sense mathematically. And I put my hand up and said, I know people simulate it. And he said, well, they can't possibly be doing it. So can I reverse the question? How are you simulating something that people don't believe is even well defined?
It's a very good question. For viscosity, I would definitely agree.
Well, that's what I didn't understand.
Stewart theory.
Yeah,
So he was talking, he said that that's not a well-defined mathematical.
It has causality problems, but there's now this VNNK, which is causally, coherent. I don't understand that.
yeah,
I mean, it's a plasma. Of course it has resistivity.
Yeah.
Must.
so I think there is even a difference between resistivity and viscosity, and that viscosity definitely has those causality problems if you do things in a naive way. But there's ways around that, either kind of more ad hoc, that you add a damping that keeps it causal, or like Elias Most has a paper coming from the Vlasov equation and developing a causal theory. And there's others. There is his last name is Koftun. He's in Canada, who has a very nice theory based on string theory principles, which I don't understand, but I invited him to try and understand this. But like for resistivity, the nice thing is that the causality problems come from the Laplacian operator, pretty much. But for resistivity, you don't need that. You can solve instead Ampere's and Faraday's law together, and then your Ohm's law doesn't have a derivative in it. So then there is no direct causality problem, but the Ohm's law is still ad hoc, and the way it's designed is like to make it. You pretty much say so you want to mimic this in the fluid frame, and then you apply your proper frame transformation to the lab frame, and then you get an additional term, and you make sure that all of it in the Newtonian limit in like v much smaller than c reduces to the Newtonian Ohm's law. That's the way it's done. So it doesn't like mathematically have causality problems, but it's definitely not first principle. If you look at Elias's paper, then he gets an Ohm's law with the resistive term that looks somewhat similar, but there's corrections to it, charge corrections, for example, which you need to take into account. So I would again turn the question around, and I'm not for resistive geometry doing fundamental physics. Still need PIC for that. But what I'm doing is doing GRMHD with a proper reconnection rate. And then I don't care too much about what's happening below the grid. Just try to capture it in an effective field theory kind of.
I think let's get Bart again. The beautiful talk.